Hello, here's the video that I promised you to finish up section 2.4. We had section 2.4 started the other day, but I'll go ahead and review what we've done. We were talking about exponential functions, and we're working our way toward log functions. Exponential functions base b have the form of f of x is equal to b to the x, where that number b can't be 1, and it has to be positive. So if I break it into the categories where b is not only positive but bigger than 1, then remember that we have a growth curve. For example, f of x is equal to 2 to the x, describes something that doubles in size over time. F of x is equal to 10 to the x, grows tenfold in size. Each x produces a y value that's 10 times larger than the previous one. When we use the base as the irrational number e, remember that e is roughly 3, e is 2.7-ish. So all of those would have growth curves. The growth curves look like these. Let me put a little grid on here. All exponential functions, growth or decay, pass through the ordered pair 0, 1, because any number to the 0 power is 1. Then if the base is bigger than 1, for instance, if the base is 2 and x is 1, the first y value would be 2 to the 1, which is 2. Second y value would be 2 squared, which is 4. So it follows that little pattern, and it grows pretty quickly. But as I plot negative numbers, 2 to the negative 1 was the same as a half. 2 to the negative 2 was going to give us a fourth. No matter what negative number I get in there, I'm going to get some sort of fraction out of here that's never 0 and never negative. That's what I mean by a growth curve. The decay curves occur when the base is between 0 and 1. So the one we did the other day in class was 1/2 to the x. But anytime there's a fraction in there between 0 and 1, you're going to get the opposite thing happening. That when the exponent is a positive number, the y values are going to get smaller, 1/2 to the first compared to 1/2 squared, compared to 1/2 cubed. Those y values get smaller and smaller and smaller. And if the exponent's negative, that means to first flip the base and then put the power on it. So those values are going to get bigger. They'll still go through 0, 1, but the graph is going to be big over here and dropping as you read from left to right, but never, ever negative. Those are the decay curves. So if I were to draw the graph of f of x is equal to e to the x, then the values that this thing passes through, if x is 0, e to the 0 is 1. If x is 1, e to the 1 is e. X is 2 gives me e squared. X is negative 1 gives me e to the negative 1, or 1 over e, roughly a third. So I'm just going to repeat the graph that I had in the first part. 0, 1 is here. 1e. So if I go up to e, e is not quite 3. 1, 2, there's e. E squared is going to be not quite 9, but it's going to be pretty big way up here. 1 over e. It's going to go through these values right here. So let's list some of the properties that we see. We listed them the other day, the properties of the exponential function, starting with the domain and the range. The domain of an exponential function is the values of x that I'm allowed to put in for the exponent. And I can put in any number I want. So the domain is the set of all real numbers. But these graphs lie strictly above the x-axis, which tell us that the range is all y values strictly positive. All of these pass through 0, 1. And they're one-to-one functions. They'll pass the horizontal line test. One-to-one functions mean that if b to 1 power, let's say to the m, is equal to b to another power, bases are the same, then that can only happen if the powers are equal. Another byproduct of one-to-one functions is they have inverses, and that's where logarithms are going to come in. Some other properties of exponential functions are going to be properties of how we manipulate exponents. For example, any number to the 0 power is 1. We already said that when we said these all pass through the ordered pair 0, 1. Any negative power can be computed by flipping the base and then making the power positive. When you multiply like bases, you add the exponents. When you raise a power to a power, you multiply exponents. And when you divide, you subtract exponents. So you can combine exponential functions in that way. Excuse me. So if we had a few exponential equations, for instance, similar one to what we did the other day, was something like 3 to the x minus 1 is equal to maybe something like 81. You can start putting in powers for 3 to see when I hit 81. So let's see, 3 to the first is 3. 3 squared is 9. Times 3 is 27. 27 times 3 is 81. So 81 itself is 3 to the fourth. So I'm going to replace the 81 with 3 to the fourth. Then the one-to-one property says that 3 to a power is equal to 3 to a power only if the two powers are equal. So now I can ignore the 3's and set the two powers equal to one another and solve for x. So this particular equation has a solution that x is 5. If I have something like, let's see, let's try 16 to the x is equal to maybe 32 to the 2x plus 1 power. There's several ways you can look at this one. I know 16 divides into 32, but I can't write 32 as a power of 16. I can write both of these as powers of 2. 2 to the fourth is 16, 2 to the fifth is 32. So that's what I'm going to do first. Write this as 2 to the fourth raised to the x power. And write this as 2 to the fifth raised to the 2x plus 1 power. Now we use the property that when you raise a power to a power, you multiply exponents. And we can rewrite this as 2 to the 4x is equal to 2 to the 10x plus 5. Now we have the same situation we had in the previous problem. We can just equate the exponents. 4x is equal to 10x plus 5. Let's get the x's together by subtracting 10x from both sides. And then divide by -6. And our answer is -5 divided by 6. So our strategy here is if we can write the bases as powers of the same number, then let's do that. However, we will often encounter equations like this. Say 3 to the x is equal to 5. That equation has a unique solution. 3 to the x is a growth curve. And then y is equal to 5 is going to cross there. So here's the solution we're looking for, but I can't get it by these ordinary algebraic means. There's no way to write 3 and 5 as powers of the same number. So here's where we're going to whip in our definition of the logarithm. We need a logarithm. And I'm going to go to the next page and get you one. We'll solve this equation a couple ways in a few minutes. Another version of this equation would be something like 2e to the x minus 1 is equal to 6. I can rewrite this equation so that I can get the e to the x by itself. 2e to the x can be written as 7. Get the 2 over there. E to the x is 7 halves. But again, in this step, we need a logarithm. There's no algebra to peel away the exponent. So we define what that exponent is. We define that exponent that goes on a base b to give us a value on the right-hand side as the logarithm of that exponent, base b. We write that the logarithm, base b, of a number x is an exponent y if and only if b raised to the y power gives us x, where this b is the same b as it was in the exponential function. It's a number that is not 1 and it's bigger than 0. This is the inverse of the exponential function base b. So if I define f of x is equal to b to the x, and I know it's 1 to 1, then I know it has an inverse. And how do we get the inverse of a function? We take the y and call it x. We take the x and call it y and solve for the new y. So let's do that. We would write this y value as an x, this x as a y, and now solve for y. And there it is. Y is the logarithm base b of x. So let's bump back to this equation above that 3 to the x is equal to 5. Look at that over here. That number x is going to be the logarithm base 3 of the value 5. Okay, whatever number's on the right-hand side becomes the exponent on the base to give us the value of the logarithm. Or what we've just said here, if I were to substitute this back in, is that 3, now put that in where the x is, to the log base 3 of 5 is 5. The exponential function, base 3, and the logarithm base 3 undo one another. In other words, f of f inverse of x gives us back x, and the other way around as well. We'll see that f inverse of f of x will give us back x. We'll use the fact that a logarithm is an inverse of an exponential function to sketch a graph. I'll also refer to this definition to help me sketch a graph. So let's sketch a graph of a log function. Let's pick a particular base. Got a little too many and ofs here. Let's look at f of x is the logarithm base b of x for a base that's bigger than 1. So the log base 3 of x or the log base 2 of x, those would all be examples. log base 2 of x. The function that I'm going to graph, if I look at it in this form, I would write y is equal to the log base 2 of x if and only if 2 to the y gives me x. And now I'm going to plot some points. But I'm going to put y's in and generate the x's. If y is 0, x is 2. If y is 1, if y is 0, x is 1, silly. 2 to the 0 is 1. But now, if y is 1, x is 2. If y is 2, x is 4. If y is -1, 2 to the -1 gives me a half. So I'm going to plot those over here on a grid. But I'm going to plot them as the ordered pair xy. So in other words, I'm going to plot x is 1, y is 0. Well, that's right here. X is 2, y is 1, would be about right here. And x is 4, y is 2 is about here. X is a half brings me down 1 unit, and then all of the other fractions will continue to bring me down those units. So this will be the graph of a logarithm base 2 of x, or a logarithm base b of x, where any number bigger than 1 can play the role of b. Think about how we graph inverses. We reflect them about the line y is equal to x. If we reflected this, I'll draw you in red the exponential function that was the growth curve. That's the growth curve b to the x. You can see how the graphs reflect about the x-axis. If the base is going to be a number between 0 and 1, then we would reflect the graph of our decay curve about the line y is equal to x. So here's the graph of f of x. Oops, don't want that. I don't want that. F of x is equal to log base b of x if the base is between 0 and 1. It is still going to go through the ordered pair 1, 0, because on every exponential function, we have the ordered pair 0, 1. Flip that ordered pair, and you go through 1, 0. The exponential function that was a decay curve drops and then becomes real close to the positive x-axis. Flip that around, this is going to be real close to the positive y-axis, and then come around like that. Of course, it's going to go right through here, but it's going to be the reflection. I'm going to draw you in red again about the line y is equal to x of our decay curve. The decay curve looks like this. So this piece up here is what's being mapped down to this piece underneath the x-axis. And then this piece right here flips up to this portion above. So you're either going to get a curve that looks like this if the base is between 0 and 1, or a curve that looks like this if the base is bigger than 1. Okay, so we're going to practice using this definition to compute some logarithms. For instance, let's compute a logarithm base 3 of 81, because we kind of just did this a minute ago. The logarithm base 3 of 81 is an exponent that goes on 3, so that 3 to that power gives us 81. The one we did a minute ago was this one. 3 to the 4th is 81. So the value of this logarithm is 81. Sometimes we have to do a little bit more work. For instance, suppose I have the logarithm. Let's go with a base 16 of the number 2. Applying the definition again, The logarithm base 16 of a number 2 is an exponent that goes on the base to give us the value of the logarithm. 16 to what power is 2? So I'm going to write it from its log form to its exponential form to see if I can figure out what that power is going to be. 16 to what power is 2? Right off the top of my head, I don't know. But I do know that 16 can be written as 2 to the 4th. So I'm going to write that now and write that as 2 to the 4th to some power is 2. And when you raise a power to a power, you multiply exponents. So that says 2 to the 4 times this mystery number is 2. This is 2 to the first power. I've got my exponential functions written in terms of the same base, so that means I can equate my exponents. 4 times that mystery number is equal to 1. Equate the exponents. So that number that goes in the box is going to be 1/4. 16, log base 16 of 2 is 1/4. We do have a common logarithm. We have two common logarithms. We have a logarithm base 10 that's a common logarithm, and a logarithm base e that's a common logarithm. So before I do some more examples down here, let's squeeze those in right over here. Our common logarithms. These are the ones that are on your calculator. The logarithm base 10 finds exponents that go on 10 to give us a particular value. The logarithm base 10 of a number x is an exponent y, if and only if 10 to the y gives us x. But we never write the 10 when we talk about logarithm base 10. We instead just write the word log. So when you see that sentence, log of x is equal to y, that means find that number, y, that goes on 10 to give us the x. When the logarithm has e, that Euler's natural number, as its base, the logarithm is called a natural logarithm. So if I write it with the letter e down there and apply the definition, that's looking for an exponent that goes on the number e to give us x. But again, we never write log base e of x. We write natural logarithm, which is abbreviated ln of x. So when you read that sentence, you convert it to the exponential form e to the y is x. We're going to love natural logarithms. We're going to use them all over the place. These things help us find exponents. It's going to be a pretty important tool. We've got a little thunder going on outside. I bet you guys can hear it through this recording. So I'm going to go back up and calculate a couple more logarithms. Let's look at a logarithm base 10. So I'm going to back up where I left a gap on the previous page and see if you can compute the log maybe of 1,000. And then let's multiply it with the log of 0.1. I'm not thinking I'm going to fit a fourth example here, so let's hide that. Okay, so the log of 1,000, reading this line down here, says find me an exponent that goes on 10 so that 10 to that power is 1,000. The nice thing about logarithms base 10 is you can just count the zeros. There's 3 zeros on 1,000, so the log base 10 of 1,000 is 3. 10 cubed is 1,000. So to figure out the next number, I want to know 10 to what power is 0.1? Well, it's easier to see if you think of 0.1 as 1/10. Now I know what the power has to be, and I need a power that'll flip my base. So that power is going to be a -1. And now in this example, I just multiply these two together and get -3. Okay, a logarithm is an exponent, or a logarithm can be used as an exponent finder. I'm going to go back and show you how we can use a logarithm to find this after we talk about the properties of log functions. Let's kind of mirror the way we wrote the properties of the exponential functions. We first mentioned domain and range. The domain of an exponential function becomes the range of the log function. So the range of the log function is all real values y. Look at the graph. I've got positive y values, negative y values, and even got y as 0. But now both of these graphs of log functions are strictly to the right of the y-axis. The domain then tells me that x is strictly positive. All of our log functions pass through 1, 0. So the logarithm, any base of the number 1 is 0. You can figure that out, right? B to the 0 power gives you back 1. Any logarithm of 0, any logarithm of 1 is going to be 0. Logs are one-to-one functions. Because they're inverses of exponential functions. So that says if you have a logarithm base b of one item equal to the logarithm same base of another item, the only way that can happen is if the articles of the two logarithms are equal to one another. We'll use that to help us solve some log equations. Logs are inverses of exponential functions. So if I take a logarithm base b of an exponential function base b, those two rules peel each other off and give you back x. And the other way is true as well. If I have an exponential function base b, but in the exponent we put in a logarithm base b of a number x, then those rules cancel each other out and give you back x. Logarithms come from exponents. So there's 3 special properties of logarithms that's probably not going to fit in this little bitty box that I have left. So I'm going to try to make some room here. Let me write this one down. A logarithm, I'll just use a log base 10, but it's true for log base b, natural log, any logarithm. Just save me writing that little subscript. A logarithm comes from exponents, right? A logarithm is an exponent, actually. So it has properties that mimic the properties of exponents. Like when you multiply like bases, you add exponents. So if I put a product of 2 exponents in here, that can come from multiplying. You add exponents when you multiply. Say that again. When I multiply like bases, I add the exponents. So I can write this as the log of m plus the log of n. Let's move this out of the way a little bit. Let me move this up a little bit. Got a runaway n up there. Let's just get rid of it. The next log property, I'm going to put m divided by n here. When you divide exponential functions of the like base, you subtract exponents. So that's what it's going to look like over here. I'm going to take the exponent that is the top minus the exponent that is the bottom. And then the one that mimics raise a power to a power looks like this. The log of m to a power can be written as that power times the log of m. Now let me move that back down a little bit. Not going to work for me because I moved it too far. There we go. There we go. Okay, now let's look at some basic log equations. The first one, let's look at a logarithm base 5 of x is equal to, how about -3. I want to know what x makes this -3, or what x makes this statement -3, and what we're going to use is our definition of the logarithm. A logarithm has its log form and exponential form. I can peel this logarithm away just by swapping it out to exponential form, which says take the base, raise it to the right-hand side, that'll be equal to the article of the logarithm. So our solution will look like 5 to the -3 is equal to x. I can go a little bit further. 5 to the -3 means 1 over 5 cubed. 5 times 5 times 5 is 125. So this has as its answer, x is equal to 1 over 125. So one way to try to solve a log equation is just to change it to its exponential form. Now, if you have something like this, say a logarithm, let's put that back in black again, and I'll do the answer in blue. Suppose we have a logarithm base 3 of x plus 4, and that's equal to a log base 3 of 5x minus 8. Now I don't want to change things to exponential form because I have the one-to-one property. The one-to-one property that I have up here. I have a log base 3 on the left equal to a log base 3 on the right. And the only way that can happen is if the articles of the logarithms are equal to one another. So by the one-to-one property, we can get rid of the logarithms and say that x plus 4 has to be equal to 5x minus 8. And now solve for x. Let's subtract this x from here to get 4x. Let's add 8 over here. 8 plus this 4 gives me 12. And so that tells me that x has to be 3. Okay. All right, let's put a few more logarithms in here. Let's try something like let me make one up here. Why didn't I have one ready for you? Let's go with the logarithm just do regular log, base 10 log. Log of x plus the log of let's try x plus 3 is equal to, let's just put a 1 here. Let me see if I can do this. Let me check it out in my head real quick. Yep, that one's going to work. Let's try this one. I'm going to try to mimic what we did in problem number 1. Get a single logarithm on the left side and a number on the right, and then change it to exponential form. And I know I can take several logarithms and put them together as a single logarithm because I have these 3 special properties. Let's look at the first property that I have. This says that the sum of 2 logarithms can be put together as a single logarithm by multiplying the articles. In other words, I can put these 2 together as the log of x times x plus 3. Now change it to exponential form. This is a logarithm base 10. So in exponential form, we have 10 to the 1 is equal to the stuff here in the parentheses. So 10 to the 1 is equal to x squared plus 3x. Let's go ahead and get a 0 on one side. And this is what I had to check if I'd get something that I could factor. And sure, we can find factors of 10 opposite in sign that add to a positive 3. How about 5 and 2? And to get the positive 3, we'd go this way. And now we would set each factor equal to 0, and I'd get x is negative 5 and x is positive 2. But now we've got to be a little bit careful because remember the domain of a logarithm. X has to be positive. Look at this one here. If I stick that in for the x, I've got something that's not defined. So throw it away. X is equal to 2 is the only solution that matters to us. So we keep that one. X is equal to 2 is our only solution. All right, I left lots of room, So let's jump down. I don't have room to solve something in there. Let's put a log equation right here. How about we go with the log? Let's go base 2 of x plus 1 minus the log base 2 of x minus 3 is equal to, how about the log base 2 let's try x. I might have to change things. Let me kind of work this in my head here. Oh, I don't know if this is going to work. Maybe. Oh, let's try it anyway. Let's go from here. I put the minus sign here so we can use the other log property that we have up here with the subtraction. I can put these 2 logarithms together as the log base 2 of x plus 1 divided by x minus 3. And now I have the log base 2 of x here. That says the logarithm on the left is equal to the logarithm on the right. They're both log base 2s, so I can get rid of the logarithms. The one-to-one property says that x plus 1 over x minus 3 has to be equal to x. All right, let's solve this for x. Let's hope I've got something we can factor. If not, we've got a quadratic formula. The quadratic is going to come into play because I'm going to multiply that denominator with the x. And I have x plus 1 is equal to x squared minus 3x. Now let's get a 0 on one side. Put the 0 here, and I'll have x squared minus 4x. See, that 1's trouble. Let's see, if this were 5, let's go back up here and doctor this up. Let's change this to a 5. That was easy enough. That would make that a 5 and that a 5. Nothing else would change. But now when I move that over, I would have a minus 5 here. And that gives me something I can factor. Right? There are factors of 5, opposite in sign, that add to -4. And they are x minus 5, x plus 1. And so we get two solutions. X is 5, x is -1. But again, I can't take the log of a negative number. So this one goes in the garbage. We keep that one. All right, so now let's go back to the equation we had a minute ago. We had 3 to the x is equal to 5. And the exact solution of this equation was, by definition, that exponent is called the logarithm base 3 of 5. But that's pretty worthless. If I want to get the decimal approximation of this and I whip out my calculator, there is not a log base 3 on there. There's only a log base 10 and a natural log. So let me show you how we can get a solution that we can approximate with our calculator. So here's another way. Take the natural log of both sides, or any log, but I like the natural log because it has the least number of letters in it. How about that? The reason I wanted to do that was we've got this log property up here that says if I take the log of something to a power, I can pull that power down in front. I can take this x from here and pull it down in front there. And now we have this equation, x times the natural log of 3 is equal to the natural log of 5. Both the log of 3 and the log of 5 are numbers we can get on our calculator. They're irrational numbers. So I can just divide by the natural log of 3 and write my solution like this. 3. So let's take a look at them side by side. The other solution, x, is the natural log of 5 over the natural log of 3. These two numbers are equal to each other. In fact, there is a change of base formula that looks like this. That if I have a logarithm, base b, of some number here, I can compute it by taking the natural log of that number divided by the natural log of the base. You can also do this with any logarithm you want. I can use log base 10s over here. I can use any log I want. So the other equation that I had earlier on that I didn't solve was the 2e to the x minus 1 is equal to 6. We can move it around to get e to the x is 7/2, and now let's look at solving that equation. So let's start from the beginning. 2e to the x minus 1 is equal to 6. Start the same way. Get the exponential function by itself. Divide by 2. And now let's take the natural log of both sides. We'll have the natural log of e to the x is equal to the natural log of 7/2. But remember, the logarithm and the exponential, the logarithm, natural logarithm, and the exponential function base e are inverses of one another. So all you get out of this over here is x. And there's our answer. X is the natural log of 7/2. So that's going to be a really handy tool for us. When we need to solve for an exponent, we'll take the log of both sides. We do have to make sure we have a single term. I could not have taken a log of both sides from this step. I've got to get the exponential function by itself. There's not a distributive property for logarithms. So warning. If I have a logarithm of two things added together, that's not equal to the log of the first plus the log of the second. Because remember, the sum of two logarithms is the log of a single product. I I can't distribute that through here. I didn't mean to write natural log here. Let's go with the log log and stay consistent. Same true with there's no distributive property whatsoever. That's not equal to the log of the top divided by the log of the bottom. Okay? And when the power is on the article of the logarithm, there's a difference between this. That implies that the power is only here. That's not equal to this. Right? When the power's here, then we can bring it down in front. When the power's out here, we can't bring it down in front. So be careful with how you use your log properties. Make sure they look just like the ones that we have written earlier. I believe that's the end of this, so let's see if I can get this to you, and hopefully you can make your way through it. I may have talked pretty quickly because I wanted to keep this short, but when you're watching the video, you can pause it, get you a cold drink, restart it again, but try to understand these log properties and how we can use them to solve equations.